The next topic is the optical isomerism in halogen derivatives. Now, last year we studied the stereoisomerism, and it is the part of stereoisomerism. Optical isomerism is the part of stereoisomerism. As you know that when we consider the optical isomerism, in that case these molecules, those molecules which are having the same molecular formula, same bond connectivity, that is the structural formula, but the spatial arrangement of atoms or groups, if it is different, then such type of isomerism is called the optical isomerism. It means in the optical isomerism, the spatial arrangement of the atoms around a particular atom is, if it is different, then such type of molecules are called the optical isomers. Now, why there will be need to study the optical isomerism? Because to understand the nucleophilic substitution reaction, so for that the optical isomerism is required, and therefore we are taking the optical isomerism. To understand the concept of optical isomerism, we have to understand some terms by which we can easily understand the concept of optical isomerism, and therefore one by one we are taking these terms. And therefore the first term which is important to understand the optical isomerism, it is the chirality. Now for that, consider the simple example to understand what is the chirality. It is the 2-chlorobutane, and when we are taking an example of 2-chlorobutane, if you observe, there are 4 carbon atoms. Out of the 2 are terminal carbon atoms and 2 carbon atoms are middle. If you observe the second carbon atom, on which I am giving the asterisk, it is found that to this carbon atom one hydrogen atom is attached, one chlorine atom is attached, one methyl group is attached, and fourth one is the ethyl group attached. It means it is found that to this carbon atom all the 4 groups or atoms are different, and therefore this is called a chiral carbon atom. If any atom which is attached to 4 different groups or atoms is called a chiral atom, and therefore this carbon atom is called the chiral carbon atom because to this carbon atom all the 4 groups or atoms are attached are different, because to this carbon atom one methyl group is attached, one hydrogen is attached, one chlorine is attached, and one ethyl group is attached. All the 4 groups or atoms are different. One is hydrogen, another is chlorine, another is methyl, and fourth one is the ethyl group. So all the 4 groups are different, and therefore we can say that this is the chiral carbon atom. And this chiral carbon atom is important when we consider the optical activity. The which compounds can show the optical activity, phenomenon of optical activity? Those molecules which contains the chiral carbon atom, that shows the phenomenon of optical activity. Because if there will be a presence of chiral carbon atom, then the isomers of such type of molecules are having a non-superimposable mirror images of each other. It means if we are taking a mirror image of particular isomer, and that mirror image, if we are superimposing on each other, then these are non-superimposable. It means that not superimposed. For example, if we are considering my hand, if I am taking a mirror image of the left hand, it is nothing but it appears like a right hand. Now if I am considering this right hand is the mirror image of the left hand, in that case if I am superimposing these 2 palms over each other, you can find out that these are non-superimposable because the fingers that matches are different, and therefore such type of condition will be occur when we are considering the molecules which are having a chiral carbon atom. For example, in the 2-chlorobutane, this is the chiral carbon atom, and that is the arrangement, three-dimensional arrangement, actual arrangement of the molecules, that is the three-dimensional. In that case, methyl group attached to this carbon, then hydrogen is attached, then ethyl group, then chlorine. Now I am taking the mirror image. The mirror image appears like this. This is the second structure. Now this is the mirror image. Now I am taking this mirror image of this molecule and I am superimposing on this molecule. I am taking on this molecule. What happens? This methyl group matches this methyl group. This carbon matches this carbon. But on the right hand side of the carbon there will be a chlorine. But in the mirror image it is hydrogen. That does not match. Then on the left hand side there will be hydrogen in the original molecule. When we are considering the mirror image, it is the chlorine. Hydrogen, on hydrogen there will be a chlorine atom is coming, and therefore these are called the non-superimposable mirror images of each other. And when any molecules such showing non-superimposable mirror images of each other, then such molecules are having a chiral carbon atom, or we can say that the molecules which are having a chiral carbon atom, that does not having the superimposable mirror images, and therefore we are getting the two different isomers. It means the spatial arrangement of these two isomers is different, though these are having the same molecular formula, same structural formula, that is the bond connectivity is same, but these are having the different spatial arrangement. Now what is the spatial arrangement? When we are considering this carbon or this example of 2-chlorobutane to this carbon atom, the chlorine is attached to the on the right hand side. But when we are taking the another isomer of this 2-chlorobutane, in that case on the right hand side of this chiral carbon atom there will be a hydrogen. It means the spatial arrangement around the carbon atom is different. And if we are considering such type of phenomenon, that will be shown in the optical isomerism. It means the isomers which are having the same molecular formula, same structural formula, but are having a different spatial arrangement are called the stereoisomers, or called optical isomers. These are called the optical isomerism, which is one type of stereoisomerism. Now that is one of the conditions to show the optical activity. Now the second concept that we have to consider, it is the plane polarized light. Now which is called a plane polarized light? When we are considering the ordinary light propagate in the space in a particular direction, and these are associated with the electromagnetic oscillations or electromagnetic waves, that is the electric waves as well as the magnetic waves. And these electric and magnetic waves, if we are considering this is the ordinary light propagate in the space in the form of waves, and these are associated with the electric field as well as the magnetic field. There is the electric waves as well as the magnetic waves, which are oscillating in a direction which is perpendicular to each other and also perpendicular to the direction of propagation. If we consider this is the electric wave, this is the magnetic waves. Now when we are considering the such type of ordinary light, that ordinary light oscillates in all possible directions that I am showing here in the diagram. Now when I am passing this ordinary light through a nickel prism, what happens? The emerging light vibrates in only one plane, which is perpendicular to the direction of propagation. The direction of propagation, this is the direction of propagation. Now when I am passing this ordinary light which is oscillating in all directions, when I am passing through a nickel prism, it vibrates or it oscillates only in one direction, which is perpendicular to the direction of propagation, which is this is the direction of propagation, and now it is oscillating in only one plane. Such type of light is called a plane polarized light. It means the light which oscillates only in one plane is called a plane polarized light. Now the concept of plane polarized light is important to know, the optical activity of a particular compound, whether the given compound is optically active or not. That we can decide by performing an experiment by passing the plane polarized light through a solution of that compound, and then we can determine whether this compound is optically active or not. So for that the requirement is the presence of plane polarized light. In that way we can convert the ordinary light into the plane polarized light. Now the next concept is the optical activity. By considering the chirality and plane polarized light, these are the basic terms when we want to understand the optical activity. So as you know that what is the optical activity? It is the phenomenon in which the molecules are having the same molecular formula, same structural formula, but the spatial arrangement of the atoms or groups around the chiral atom, it is different, and such type of phenomenon is called the optical activity. Or it is the phenomenon in which when we pass the plane of plane polarized light through a solution of certain optically active substance, then it rotates the plane of plane polarized light towards the right or towards the left. Such a phenomenon is called optical activity. To understand, consider the simple example. I am taking a aqueous solution of glucose. In a container I am taking a aqueous solution of glucose, and through this I am passing a plane polarized light. This is the plane polarized light, and when I am passing the plane polarized light, I am found that now this aqueous solution of glucose is having a chiral carbon atoms, and therefore it is the optically active molecule. And when I am preparing an aqueous solution of the glucose, and when I am passing the plane polarized light through it, the emerging light is found that it rotates the plane of plane polarized light towards the right or towards the left. Now which type of isomer is present in that glucose, on that it is depend whether there will be a rotation of the plane polarized light towards the right or towards the left. And such type of phenomenon is called the optical activity. It means when the plane of plane polarized light passes through a substance which is optically active, which rotates the plane of plane polarized light, such type of phenomenon is called optical activity. Now any isomer of a optically active molecule, if rotates the plane of plane polarized light towards the right, it is called a dextro-rotatory molecule, or it is called a dextroisomer. Understand? The any isomer which rotates the plane of plane polarized light towards the right hand side, towards the right, then it is called a dextro-rotatory, which is represented by D or plus sign. Now any isomer which rotates the plane of plane polarized light towards the left, it is called a levorotatory, which is represented by the L or the negative sign. So if I am considering this is the aqueous solution of glucose which contains only dextro-rotatory molecules, then it rotates the plane of plane polarized light only towards the right, then I can say that this solution contains the dextro-rotatory isomers of glucose. Now if it rotates the plane of plane polarized light towards the left, first it is vertical, now it gets rotated towards the left, then such type of isomer is represented by is called a levorotatory, and it is represented by L or by the negative sign. Now when we are considering the dextrorotatory and the levorotatory molecules, these molecules must contain, to show the phenomenon of optical activity, what is the condition? They must contain a chiral carbon atom, and if there will be a chiral carbon atom, these are having a non-superimposable mirror images of each other. These are having the non-superimposable mirror images. So that is about the phenomenon of optical activity. Now next we have to consider the enantiomers, which are called the enantiomers. These are the optical isomers. So the molecules or the isomers which rotates the plane of plane polarized light towards the right or towards the left by a same angle but in opposite direction are called the enantiomers. It means the isomers which rotates the plane of plane polarized light towards or in the opposite direction but by the same angle, then such type of isomers are called enantiomers. Enantiomers are having a non-superimposable mirror images of each other. Now if we are considering this example, in that case the glucose after passing the plane polarized light, the emerging light is rotated towards the left. For example, it is by a angle 30 degree. Now I am taking another aqueous solution of glucose and from that I am passing the plane polarized light. Now it rotates the plane of plane polarized light towards the right hand side. It is by a 30 degree. Now the rotation is towards in the opposite direction. First isomer rotate the plane of plane polarized light towards the left, and second isomer rotate the plane of plane polarized light towards the right, but the angle of rotation is same, it is 30 degree. It means the magnitude will be same. Then such type of isomers called the enantiomers. The isomers, optical isomers which rotate the plane of plane polarized light towards the right or towards the left, or which rotates the plane of plane polarized light in opposite direction but by the same angle are called the enantiomers. Now enantiomers, that is the isomers, one isomer rotates the light towards the right hand side, another isomer rotates the light towards the left hand side or towards the left, and therefore but by the same angle. And when we are considering these enantiomers, enantiomers are having the same physical properties. Now why these are having the same physical properties? Because enantiomers having the same molecular formula, same structural formula, there is the same connectivity, same bond connectivity. What is the difference? Only difference is that the spatial arrangement of the atoms or groups around the chiral carbon atom is different, and therefore the physical properties of enantiomers such as boiling point, melting point, refractive index are same. But when we are considering the chemical properties of enantiomers are same towards the optically inactive reagent. Now which are called the optically active and optically inactive compounds. Optical active compounds are those compounds which are having a chiral carbon atom and which rotates the plane of plane polarized light towards the right or towards the left. Such type of isomers, such type of molecules or such type of compounds are called the optically active compounds. And which are called the optically inactive compounds, the compounds which cannot rotate the plane of plane polarized light towards the right or towards the left. It means there will be no rotation. Then such type of compounds are called the optically inactive compounds. Now when we are considering the chemical properties of enantiomers, the chemical properties of enantiomers are same when we are using the optically inactive reagent. But when we are considering the chemical properties of the enantiomers towards the optically active reagent, these are having a different products or different chemical properties. It means if we are taking any enantiomer or any optically active compound and I am reacting this optically active compound with the another optically active compound, in that case the products obtained are different because both are optically active. But when I am treating the optically active compound with the optically inactive compound, the product obtained will be the same. So that you have to remember the enantiomers are having a different chemical properties towards the optically active reagent. Next, we have to consider the racemic mixture, or it is also called a racemic modification. Now, an equimolar mixture of the dextrorotatory and levorotatory isomer is called a racemic mixture. Equimolar, it means in the which are having the same, if we are taking the same molecules, same molarity of that solution, we are taking the same number of molecules of dextrorotatory and the levorotatory molecules, and I am mixing with each other, and then I am passing the plane polarized when I am passing the polarized light through that solution, it does not rotate the plane polarized light towards the right or towards the left. Such type of mixture is called a racemic mixture. It is the equimolar mixture of the optically active isomers. Now, when we are considering the racemic mixture does not rotate the plane polarized light towards the right or towards the left. It means the racemic mixture is optically inactive. Now, why it is optically inactive? Because the racemic mixture contains the both type of isomer, that is the dextroisomer as well as the levoisomer, and in the same amount, and therefore one isomer cancels the rotation of the another isomer, because the angle of rotation is also the same. It means one rotates the plane polarized light towards the right when I am passing the plane polarized light through a racemic mixture. One rotate towards the right and other rotates towards the left by the same angle. It means if I am considering the dextroisomer rotate the plane polarized light towards the right by a 30 degree, then what happens? There will be a presence of levoisomer which rotate the plane polarized light towards the left by the same angle, and therefore it becomes its original position, and therefore there will be no rotation, and therefore we can say that racemic mixture is optically inactive because the dextroisomer and levoisomer cancels the rotation of each other, and therefore it will become the optically inactive. So that is the concept of optical activity.